Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the next session. My name is David Heckerman, and I'll be your host. There are two groups at Microsoft Research doing work in eScience and also science. And today we'll hear three talks from these various groups. We'll begin by hearing from Martin Kelson, who's at Cambridge MSR, and he'll talk to us about the Vedea Visualization Language. Martin, take it away.
Thank you. I'm going to talk to you about Vedea. Vedea is a Romanian word. Vedea is the name of a river. If you say it as Vedea, it's the name of a river. Vedea is also a verb. It means to see and to understand. So the reason for picking this is because we're all about visualizing a river of data, understanding what we see within it. The motivation for creating Vedea was I work in a part of Microsoft Research in Cambridge called the Computational Science Laboratory. In the Computational Science Laboratory, we have computational biologists, systems biologists, computational ecologists, and a tools and technology group. And I work in the tools and technology group. And we created something called, internally, what we call Discovery, the Microsoft Computational Science Studio. And it's an application that we use on the desktop that allows us to build complex data flows, complex experiments, share them, collaborate over them, and visualize the results. But what we discovered in building this was that we within Microsoft didn't have the visualization components that we really wanted. We had Excel charts and we had PowerPoint and Visio and so forth, but we didn't have the things we needed to visualize data. If you look on some of the websites that are showing the best in infographics on the web, things like infoaesthetics.com, you're not going to see a whole lot of Excel charts up there. So we wanted to get to this next level of visualization with our computational tool. Well, what does that require? What does that mean? Well, functional visualizations are more than just calculations. We have languages for doing calculations. We have languages for doing statistics, but you need a visual language. And that visual language has to give you the mechanism for expressing things in terms of color, for instance. I have a Gaussian hotspot map here. How do you get a Gaussian hotspot map over the top of virtual Earth, for instance? We have to have an alphabet of vocabulary for expressing shape as it relates to data. We have to have the verbs and mechanisms for expressing data in terms of line. Here we have a network diagram. And in terms of hierarchy. Now when you bring all those things, and composition. Composition being simply that we may know how to present our data, we may be able to get it up there, but how do we compose it in a fashion that's both visually instructive and a pleasure to look at. When you bring all those things together, you need to have a language that allows you to bring them all together so that you can express color, shape, line, hierarchy, and express the relationships of those things to your data and result in some sort of meaningful graphic. And that was our goal with Vedea. So who is this all for? If you look at the existing systems, if you look at what we offer right now, we have WPF and Silverlight, and in the 3D arena you have XNA and OpenGL. That's really the domain of the skilled developer. Right? There's some heavyweight APIs to learn there, a huge surface area to these APIs. It's a lot of work to become skilled at these and get things looking the way you want them to. Then as a second option, we have processing. You may have encountered processing. It's by Ben Fry and his collaborators out of MIT. You can download it for free off of processing.org. It's very suitable for nascent developers, sort of people who are beginning to do some programming, and for skilled developers. It's based on Java, and I'll talk a bit more about processing through this talk. And then you have Excel charts, PowerPoints, and Visio. The target there really are domain experts and chart composers who are not necessarily developers. There's no programming involved. There's usually no programming involved in generating things there. But the downside is these are not terribly visually expressive environments. You can tweak them, but you can't substantially modify what they are. You can't substantially modify the charts or add completely new charts. And we believe Vedea belongs somewhere in the middle here. And you see that it spreads its arms pretty wide. Well, what that means is that it's accessible to the nascent developers. It's composable by chart composers. What that means is one person can write the visualization and do the visualization work. That might be somebody who's sort of a nascent developer, a skilled developer, but they make things for the chart composer, someone who's just pasting up a web page out of pieces. They give them something that they can use as instructed then by the domain expert. So we see a collaboration up and down this scale. And yet we have a high standard of expressiveness. You can do some very visually attractive things here, and it's expressive as a language such that skilled developers don't get frustrated. You're not making them program with big mittens on, and it's hard for them to get things done. So that's the target that we have for that. The inspiration for this is the language processing. So processing is actually Java. But it's Java that's been enhanced with some very clever libraries that bring very rich visual idioms up into a flat namespace so that you don't have to remember a whole bunch of libraries, a whole bunch of API syntax. If you type rectangle, you'll get a rectangle on the screen. If you type circle, you'll get a circle on the screen. And every frame, 30 frames a second, you have to repaint your image. And so you get animation. In fact, a still image is simply a moving image that isn't animated. You have to redraw every frame, and that keeps things very simple. People understand then how to draw things in there. It's an inspiration to us because it's been extremely well taken to by infographics people and people doing science for visualization. But there's some limitations to it. It's still Java. There's nothing wrong with that as Java, but it's constrained by the Java syntax. And there are some things that we'd like to do to bring data closer to visual elements, bring visual elements and data closer together, bind them together. And we can't really do that without modifying the syntax. We can add libraries on top of Java, but to really do what we want to do, we wanted to revisit the syntax of the language. So we build on these things that we found in processing. And we have three major guiding principles to Vedea. So again, from processing, what we learned from processing, very simple, approachable programming model. It's targeted at non-CS domain experts, people who are domain experts in things other than programming. The biggest thing we learn from processing is you need results from the first line of code you type. You can't put 100 lines of code between somebody and their first visual response. You have to give them a response on the screen right off and let them evolve that as part of the development process. One of the things that we've gone one step further on is data is part of the language. That data isn't something that's bolted onto the side. Data isn't something you bring a library in to get at, but data is a first-class citizen in the language. So each one of those guiding principles now I'll go through in a little more detail. What strategy did we apply to get those guiding principles taken care of? First off, approachable programming model. Well, it's a high-level graphics, powerful high-level graphics idiom in a very flat namespace. There's not a lot of using statements. You don't have to remember a bunch of libraries. There's not a big API. Everything's kind of always there. It's a dynamic language, so there aren't a lot of rules in terms of typing. It's a strongly typed language, but it's based on the Microsoft Dynamic Language Runtime, which you can download today for free from Codeplex. Python, for instance, is a dynamic language. A number of other examples of dynamic languages. We built on that so that people get the benefit of strong typing without having to remember to declare something as a float and always use it as a float and so forth. I'll show you some examples of the impact that has. It's one language, in other words, one syntax. You write your program one time, but that then can be rendered on the desktop or in a browser. It can be in on an Apple in Safari. It can be on a PC in IE. It can be on the desktop. It'll look the same. even if we switch renderers from a 3D renderer from XNA to a 2D renderer like GDI, you get the same output. It's a standalone authoring system. You can author in a web page. It's a zero-footprint SDK. There's nothing to download to write the first program. Everything comes down in the web browser. Results from the first line of code. So if you're a developing programmer, if your field of interest is not computer science, then probably the way as a developing programmer you program is a little bit trial and error. You type something, when you're doing visual programming especially, you type something, you see a result on the screen, and then you evolve that result. So it's very unsatisfying to go into something like WPF or Silverlight, invest 300 lines of code in it to get the first few things on the screen and find out it's nowhere near what you wanted. Now you have 300 lines to think about instead of just one or two. So what we do is we start off with minimal overhead. We don't require you to do a bunch of preparatory work. And we give you high-level idioms for color, shape, and line. All of these things are things you can type in the first line of your code. Give you a visual and kinematic hierarchy. So things like network diagrams are built into the language at the top level. Kinematic relationships. If you want a box next to another box, and when you rotate one, you want the whole system to move, you can do that just with 2 lines of code. Say these 2 guys are related to each other. There are other relationships that you can inherit. Composition aids, like the Brewer color scheme. Cynthia Brewer put together something called the Color Brewer, and it allowed, it's for instance in PowerPoint when you pick a scheme, you'll get 5 or 6 colors that are nicely related to each other. Rather than sitting there and trying to pick those, you can do the same sort of thing in this language and say, I want 5 colors related, therefore print instead of projection, and I want them to emphasize the middle range, or I want them to be a continuous palette with a lot of emphasis over this range of deltas in my data. And likewise, physics and data binding are built into the language. So continuing on with the results from the first line, we have a very generous and forgiving syntax. It's not Java. We got to reinvent the language. So when you're specifying a color, all of these things are legal. I can call it red. I can use a unquoted HTML color. I can use a quoted HTML color. I can use a HSV or RGB or ARGB or RGB integer. There's actually about 25 overloads to that new color. Or if I want a black body color spectrum, you want things to go from cool to hot, and you want a nice projection from black to red. That's actually a kind of complex walk through the HSV color space. We'll give you some functions to generate that color palette automatically. And then, of course, the Color Brewer. And the Color Brewer allows you to get a palette of colors. If you're going to do a map, you could set a number of parameters, such as this is for projection on a screen. I'm going to have 12 different data items, and I want to emphasize the ends of the spectrum with more stark changes toward the ends of the spectrum. And it'll give you a map coloring palette. It gives you good results over a geographic map. So data as an integral part of the language. What that means is that data access and manipulation is baked into the language. Not just arrays and lists, but accessing things like CSV files and so forth is baked into the language. There's one API. It's based on something called Scientific Dataset, which was done in our group by Vasily Lyotsarev. And Vasily has put together a system whereby you have a single API that covers CSV files, NetCDF, HDF, all the common factors within these, and we promoted that up into the language itself. And lastly, and probably one of the most powerful things in the language, is that you can bind data directly to the visuals on the screen. So rather than having to have a loop where you query your data and then update the visuals, you can simply say the radius of this circle is bound to this piece of data on disk. The color of this circle is bound to this temperature from this row on a database. I'll give you some concrete examples of that. Here's our architecture, the obligatory architecture diagram. Basically, the blue stuff are things that we bring in from the rest of Microsoft and other APIs. In the red are the pieces of Vedea that we've added, a presentation abstraction layer, so that the language sees one consistent view of graphics. And then on top is the user code. On the side is Scientific Dataset. I'll talk in a little more depth about that soon here. So The interesting things about this architecture, it's a pretty small, lightweight download. Full .NET interop means that if you have things that were written in VB, you have things that were written in Ruby or Python, you can get at them from inside Vedea. Because it's a dynamic language, in one line you can say X gets new X cell, and you'll get an Excel sheet, and then immediately you can do things like X.sheet, subname.cell, something, and start manipulating it directly. So it's very easy to import COM objects and .NET and so on. This basically all boils down to modularity. You can persist your code, you can share it with somebody else, you can write a Vedea program and get a bucket of bits that you can hand to somebody else without having to hand them the source code and say, here's your visualization, and they can use that then. It's also very integrated with Office, so you can embed these things in Office documents, and you can use Excel as a data source. Here's a very quick example of the code. Now these are two programs that would run in processing and Vedea, and they do the same thing. They draw a white line that just goes up the screen over and over again like a little scanning line. The important things to notice here, first are, that's the whole program. There's no other decoration around this. The entire program is main, or setup. Those functions run once and only once at the beginning of your program, and then draw, or in our case update, which run one time per frame. And if you look at this code, then one time per frame, we're going to erase the background, reduce the Y by 1, and then repaint. And so you get this line that moves over and over again up the screen. The differences are also interesting. Because we come kind of from a C# world, we capitalized everything. But that's not too significant. You'll notice that float y equals 100 over here in the Java syntax, and over there we just say some variable y is 100. Everything is dynamically typed. I can assign y to a string on the next line, and there's no error. So dynamic typing basically means types change on the fly. I can do this, x gets 1, print out x, then x gets foo, print out x, and it's fine. X gets a mixture of the two, and it'll type promote things to the right type and assign them to x. This is the same sort of mechanism that Python uses, very flexible type system. Strongly typed, but dynamically typed. This might be going a little too deep. You have main and update, and they look like two functions. It's almost like programming in BASIC. What we've done is we've invisibly wrapped that in a class. And so as a nascent developer will do, they'll start with simple concepts and then realize, you know what, I need object-oriented programming, or I need some higher order concept. Turns out they were already programming in an object-oriented environment and just didn't know it because we had this invisible class wrapper on the outside. Now, I'll show you some examples in Vedea when I run the Vedea examples here and show you that, in fact, you can do real class operations. I'm going to skip forward a little bit. I want to get to some concrete examples too. This is probably the most powerful part of the language, bindings. This colon equals operator means x's radius, x.radius, is bound to y. That means any future changes in the program to y will change the radius of this visual object. Second line says x's radius is bound to the value of some mythical slider. I have a slider on the screen, and it's outputting a value. Multiplied times the temperature from a data set times some scaling factor. What that means is if that data set is a SQL database or a CSV file, and somebody edits that file, or somebody changes that row in SQL, my visual is going to change. I don't have that in a loop. I've just put it one time declaratively in the program, and I've permanently bound those two pieces together. This bottom one is a two-way binding. Foo gets bar, or foo is bound to bar. It means that if foo changes, so does bar. If bar changes, so does foo. The two are now coupled together. Now, they can be more than just simple variables. They can be complex expressions, lambdas, and so forth. I have some examples of that. I want to talk about scientific data set before I get to the next binding piece. We have a data set here that has latitude and longitude and time. So we have years of data at some array of latitude and longitude, and it's temperature data. So keep this visual in mind. This is a data set, could be a NetCDF data set. And what scientific data set allows us to do is refer to things, for instance, mydata.temperature, at some latitude and some longitude and some date, and I get a value back. Now, all the niceness in scientific data set means that I don't have to actually have data at that latitude and that longitude or that date, because we can provide interpolators and tell it to either give us discrete values or interpolated values. It'll do the right thing. What we do with scientific data set and the bindings, when you bring them together, is you have this collection binding. What this says here is, if I set the current year to 1900, and then I bind this variable circles to a link expression, that link expression says, from I in data set, for every I in data set, where the year is equal to current year, and that strange colon equals equals simply means, it's shorthand for a Boolean expression, I dot year is equal to some temporary variable x bound to current year. It's just a shorthand for saying I want this Boolean reevaluated every time anything changes in it. So what I've said here is my collection of circles gets every I in the data set where I's year is the current year, that variable current year 1900, select a new circle whose radius is relative to the population, whose color is the temperature, and whose x and y is the latitude and longitude. Now what happens if I change current year? If I change current year, the population of that collection changes. So as current year changes, if I bind current year to a slider, as I move that slider, more circles or fewer circles will appear based on what's in that data set at that particular slice. If somebody goes to the SQL server and adds or removes rows, more circles or fewer circles appear. What I've done at the last line is in my scene graph, I have a map, and I've added all the circles to that map. That's the whole program. This would give you basically circles whose color, radius, and location are dynamically bound to a data set with no iterative aspect to this program, allow you to have a dynamic interactive map. So some other things you can do with bindings. Maybe I don't want things to snap from one value to the other. I want a linear interpolated animation so things move smoothly on the screen. I might want to turn collision detection and mass on. I now have physics baked into the system, and I can do things like build physics, intuitive physics UI, things that stick together, that bounce, that have some mass to them. I'll skip this. Some of this is esoterica, and I'm definitely running out of time here. So where are we today? Today the language and the tools exist. You can run on the desktop, you can run in IE, and we have GDI and XNA renderers. We're continuing work on the bindings, animation, and drivers for more and more types of data. I'll give you some examples of this. Vedea is going to be featured in the Professional Developers Conference in LA in November. And about that same time, we'll have it available for download on the research.microsoft.com website so people can play with it. Let me give you some examples of Vedea running. That's not Vedea. That's not Vedea. What's that? That's my backyard. No. No. Okay, so here, let me do one very simple. This is Vedea Pad, which is just a little program that we use for testing the thing. Let me open up a program. I'm going to open up Dimes here. Dimes is a very short program. There's not much to it. I'll use the GDI renderer. I'll run that. What Dimes is going to do is read a database of internet traffic over a 2-day period worldwide, and it's now graphing all of the connections here. I don't have a map underneath it, but pretty quickly you can spot the population centers. You've got Australia, you've got the US, you've got Europe. It's kind of a strange wrapping of the globe. But this is a 2-day snapshot of internet traffic, simply rendered by reading the data set. You can see up here, all we did is say dataset dimes.csv, which has the data in it, Now, we didn't declare what was in DIMES. We didn't say what columns there were. We didn't say what the names of the fields were. It's a CSV file that has a name at the top of each column. And as soon as you've read it in, you can start to refer to things by the names of the columns. So this is what makes it a dynamic language, that we can create objects and mutate their member functions and their member variables on the fly based on what we read. I'll give you an example of another simple example. These aren't very sciencey examples. This is still a project in development, and one of our key tasks now is to build those WOW demos. So let's look at the tube map. This is a map of the London Underground. It's an isochronic map of the London Underground. And by isochronic, I mean that once I click on any one of these, we get these circles in a slight rearrangement. It's still geographically roughly accurate, but the spaces between stations have been moved so that each concentric circle is 5 minutes of travel time. Okay, so we get an idea of how to move there. It's a very short program. Our goal is to have Vedea programs be 25 to 100 lines long, to do significant graphics in 25 to 100 lines. I'll show you something kinematic here. And then I'm going to wrap up. I'll take one, maybe two quick questions. Something kinematic, let's look at shapes in a scene graph. So shapes in a scene graph just draws some random shapes. But what has happened here is these shapes, instead of being added to the scene, the first circle was added to the scene, the first rectangle was added to the circle, the second rectangle was added to the first, and so on and so forth. So they're all hanging off each other in a kinematic hierarchy. And if I look at what's animating all of this motion, it's essentially just a couple lines in this update function. So the first rectangle is rotating by 1 degree. The third rectangle is counter-rotating by 1 degree, which is why it looks like it's frozen along its z-axis. And the mouse move basically is just updating the position of one component, and everything else follows along. So very short programs where you can express high-order graphics concepts in just a few lines and get an interactive environment. Now, our goal here is that you be able to tackle, that you be able to connect visuals to large data sets, to ongoing experiments. One of the real goals that we have is to do simulation steering and driven experiments. If you have a map of the U.S. or a map of the world, and you have a virtual Earth type approach to it where it's broken up into 4 tiles, and as you go into successively deeper and deeper resolutions all the way down to where you can see your state, your city, your house, we would like to drive calculations at the same time. You might refine simulations at the same time that you're moving in and out of this map. So this is not an end product. This is not a visualization that hangs at the end of your workflow. It's something that you could also have as an input or a steering device in your simulation. I'll show you a couple resources here while I take questions. I have literally just, I think, 2 minutes. I recommend you take a look at processing.org. It's an excellent tool and definitely the inspiration for what we've done here. If you're interested in the types of visualizations we have in mind, Besardio.org and infosthetics.com are a couple places you can look. And visualcomplexity.com is an interesting link as well. They survey sort of very interesting presentations of information and graphics. I'll open it up for a quick question if anybody has a question. Yeah? On the left. We do, and I have, so right now I have XNA and OpenGL 3D, and the same kinematic rules apply, camera position and so forth. You can control. Yeah, so you have a camera that you can control, and into your scene graph you can also add navigators. So you might add a trackball navigator, or you might add a character following navigator and so forth. Yeah. Yeah, and I didn't talk about that, but the interactive renderers are the GDI, the HD, the ones that I've shown you here. We also can render to JPEG and PDF and a whole bunch of static forms. So you could distribute Vedea around headless, in other words, with no video screen, and have it generating JPEGs or having it, maybe you're doing multi-level virtual Earth style tiling, and you want to generate tile visualization that you can lay over Google Earth or virtual Earth. You can do that as well.
Terrific. Thank you, Martin.
Thank you.